Jai Hind all. This is Assistant Professor Gagandeep Singh from Ajay Kumar Garg Engineering College Technology, and we have discussing a VLSI technology lecture, complex lectures. This is lectures on complex topic 2. This is related to unit 1, and we have discussed in unit 1 that how important is to maintain the lattice structure of the crystal. We have discussed ingot preparation. We have discussed the impurity of the impurity in the ingot. We have also discussed how all these defects increase the defects in the ingot. So when ingot is not good, when ingot is not as per our standards, we have problems in creating the IC. So this complex topic discussed upon the crystal structure, crystal lattice structure and its defects. Generally here we are discussing about the general lattice structure, the lattice structure that is that has lattice defects that are generally seen in a lattice. So if there is any defect in the lattice, then there will be a problem in the lattice for the crystal to have the better conductivity, tensile strength, all the things, melting point, all these things are dependent upon the lattice. So we here in this lecture we will discuss the lattice structure of the silicon and how it is how it is used for the better preparation of the ingot or silicon wafer. So if we say the crystal structure a wafer, it is basically dependent upon the orientation of the Miller plane. If we say the crystal structure, if we have one triple one plane with Miller index is 1 1 1, that means that it has the maximum surface atom density. The density at the atom's surface of the lattice will be more. So when it is there are more number of atoms on the surface, then the lattice will be attracting each other and it will be easy to grow a plane over the other plane. That means the growth of this one will be higher. Also the mechanical properties will be higher because of the interaction force between the two lattices will be higher. So when the lattices attractions are higher, they are bound to each other with a greater strength. As a result, the tensile strength will be much more. However, as the number of atoms are more at the surface, so more number of oxidation atoms can attracted toward the surface. So the processing characteristics such as oxidation are the orientation dependent, and triple one plane oxides faster as compared to the other planes where we have less number of the atoms. For example, 100 will oxidize slower as compared to triple one, because they will have lesser number of atoms at the surface to interact with. So if we say there are three lattice structures in which silicon is available. One is simple lattice structure. There are atoms at the each corner. So 1 2 3 4 5 6 7 and the last 8th one, which is at the back of the plane. So there are 8 atoms at the each corner of the a box of a unit cell. Then there is a body centered where we have 8 atoms which are similar to the simple lattice structure, but one at the center of the body. So if there is a box at the center of this box, there is a one atom that is called the body centered atom. The face centered, which has one atom at the each face of the lattice is known as the face-centered lattice. So there will be one atom at this plane, one atom at the top, and one at the bottom, which can be represented like this one atom here, one atom here. So this is at the bottom plane, one at the here at the right side plane. So it will be like this one plane is one atom is this one. So this is one plane, and this is the one atom at the center of this plane box, at this plane. Another atom which is the behind this plane will be here. So it will be like here. So this is the plane where the atom is present at the back of this box. So at the each phase there is one atom in the phase. So here we can see that if we have more number of atoms, anything that will be placed over here will have more number of atoms to attract those other atoms, the atoms on the layer above this one. So there will be more number of there will be more forces on the other power. So depending upon these three types, this one, the simple one, where the atoms are at each the corner, and body centered where one atom is at the center of the corner, center of the body, and the face centered where each atom is at the face of the each box is there. We have three type of the Miller indices. These Miller indices shows that the density of the atoms in the lattice. Where the density is more, the indexes of those plane is called the Miller indices. So for body centered, the Miller indexes are 1 0 0 1 0 0. So this plane has a density of 1 0 0. Then second one is 1 1 0, where the density is at the diagonal plane. So this is the red plane where we can see that there is 1 and 2 atoms which are at the 1 1, and other plane is at the 0 x. Then third one is the other one is the face centered, where the maximum density is there and the Miller indices are 1 1 1. So here Z is 1, X is 1, and Y is 1. So all these things are at 1 1 1. So the Miller indices of this one are 1 1 1. So this is the way that we can see. This is the one at the plane where the atoms are joined, and these are at this plane which is the 1 0 0. Similarly, body centered has a one plane in between, so the maximum density would be at the diagonal planes. And last one, when there is a face centered, then the maximum density is between this atom, and this atom. So this atom has x-axis as the 1, as it is a unit plane. So unit cube. So it is 1, x-axis is 1, y-axis is 1, and z-axis is 1. So it is 1 1 1. Another thing, the same plane, 1 0 0 plane can also be taken as 1 0 1, 0 0 1. All these represent one Miller indexes, which is equivalent to 1 0 0. So the same plane will be here, same plane will be the back side of this one, and same plane will be at the end of this one, and same at this plane. So all these planes are the equal to 1 0 0. Similarly for the upper plane and the lower plane that is there. So all these planes are at the all levels which has the Miller indices of 1 0 0. So now if we see these one, there are lattice defects which can be classified as point defects, line defects, area defects, and the volume defects. We can classify it as we class point defect as 1D. This is at the one dimensional point defects. These two defects are two-dimensional defects, and the volume defects are 3D defects. So point defects, if we say, these are of the three types. One is the vacancy type, which is similar to the defect where we have we miss some atom. For example, if we have some body centered cube, and if there is a atom that is missing at the center, then it will be simple. So if there is a simple cube which is in the in the lattice of body centered cubes, there will be a vacancy at the center. So this will create a vacancy defect. Similarly, if any other atom or atom is there, extra atom is there, that is known as the interstitial effect. Interstitial defect. Now, if we join these two effects, this will result in the Franklin defect. Frankel defect. This Frankel defect means there is some atom which is not at present at its position where it should be, but it is moved to some other place. So this atom has moved to some other place. So this has also created the vacancy defect over here, as well as the interstitial defect over here. So both defects are there in the same lattice. So this defect is known as the Frankel defect. So these are the three type of the point defects. And then there is a lattice defect which are in 2D. In 2D there can be a line, or there can be a volume. So the line defects can be when we have a stacking fault. Stacking fault means when we have a one lattice which is placed over the other lattice. When this lattice is placed over the other lattice, if there is a mismatching or there is a line between the two lattices, for example, this is a lattice and other lattice is placed over here. If there is some extra line of atoms is there, so when this is placed over this one, there will be some lattice mismatch. So this will create a lattice fault. So now if we can see in the IC, if we create an IC with this defect, if some atom is placed, if some ingot is prepared with this defect, and we want to check its conductivity, the conductivity over this part will be different than the conductivity over this part. Also, the density will be here different with respect to the density over here. Here it will be more denser. When it is going to be denser crystal, there will be more chances of the precipitation. So with the precipitation, it will be difficult for material to be deposited. For example, in case of ingot preparation, in ingot preparation we have a liquid phase which is sticking to the other phase, other plane of the ingot. So with sticking will be difficult, and it will be not there as smooth as in case of the liquid silicon. Similarly, volume defects, it is also of the 2D defects, where we have 3D defects, where we have two type of defects. One is the twinning defect, and other is the grain boundary defect. In 3D we can have the area or the volume. In area we have twinning effect, which is similar, which is the extension of the line defect. Twinning is the change in the crystal orientation, or we can say that there are two different type of crystals which are the different or which are the same orientation, and they are sticking to each other. So if we see diagrammatically, these are the two crystals which have the same orientation. This has one orientation, this is a second orientation. They are sticking to each other. So this is called the twinning boundary effect. Now in this case also, again we can see that the density is not varying, but if we see as we do ingot tubing, if we want to have doping in this process, due to this twinning fault, if we want to have some doping, let's suppose we are having doping from this side, the annealing process will be will have hinder something. So this hindrance will not allow the atom to pass through this whole crystal. So there will be some collisions over here, as well as, so as a result, the annealing process here will be not as smooth as we want. As a result, the doping here will be not as per our requirement, and the twinning boundary fault will affect the whole crystal structure, crystal doping. Similarly, the grain boundary defect is there, which is extension to the area twinning defect. In this area twinning defect, in a grain boundary defect, there is a polycrystalline form. These polycrystalline form will have many crystal forms which have the same orientations. So this one is the one crystal area, this is the second crystal area, this is the third crystal area, and so on. So these are the small crystalline forms which have different grain. So these we can see that there are a number of crystals or grains that are that has different sizes. So with this one, we can see a number of problems. All the problems that we have seen in the ingot preparation will be there. There are problems of doping will be also similar to the twinning effect. There will be the material, the silicon, which is in this grain boundary defect, will not properly join with the other ingot preparation steps. Also, if we prepare the next step, which is the epitaxy, if we prepare epitaxy over this one, the crystal grown over this grain boundary property will be not as smooth as we want. So this, depending upon this one, there will be grain boundary and the twinning effect. Next one is the 3D defect, which is the volume defect. After area defect, there is a volume defect. The area, the volume defect shows basically when we have different crystal structures in the same crystal. For example, if we have 111 lattice structure, 111 lattice structure, in this lattice structure, the area where maximum density was not a straight line, not a horizontal or vertical plane. It was a slanted plane. So the density of the atom were at the slanted plane. So if there is a slanted plane, there are more chances of the atom that are joining over, or the lattice that is joining over this lattice will be slanted. For example, this is the lattice structure, which is the one with the maximum number of density, that is with the Miller indices of 111. If we join another atom, another lattice of this 111, it will be joining like this one. So this is going to be increased in the side way. So this will increase the volume where the density, where the atoms were there. So from this one, if the lattice has the maximum density over this on this plane, so this will be increasing in this way. Similarly, on the other side, it can increase like this one. So this giving a dislocation of edges, dislocations at the edges. As a result, the volume of the crystal is also increasing for the same number of atoms. Now again, we can see all the problems of ingot preparation, as well as for the doping of the ingot or the wafer. Here we have the density is changing, so the doping will be not same. Also, the crystal orientation will be different, so the all properties of the wafer will be different. So if we have an ingot with this structure, the conductivity of the lattice will be different. The conductivity over here will be different from the here, because at this point the conductivity will be in the denser material. Here the conductivity will be in the lighter material, lesser denser material. So here the area for the atom to move, electron to move, was more as compared to the movement of atom is here. Similarly, if the orientation is behind the screen, if orientation is instead of this one, if the crystal lattice orientation is on the inside direction, that means the area below this one, the lattice previous to this lattice will have will be covering more area. So as a result, there will be some skewing effect. There will be some change in the area in the volume defect. So this defect will create all the problems of the ingot conductivity, the volume of the ingot. All these things will be there. So all these were the defects which are in the lattice. Also, the orientation on the crystal are to be shown, because depending upon these orientations we can see the defects that are there. Those can be determined, as well as the orientation will also show that the conductivity, tensile strength, electrical resistivity, all these defects, all these properties of the wafer will be shown by the lattice orientation of the crystal. This lattice orientation of the crystal is shown by cutting the ingot in the planes. So if we have seen that the wafer is in a circular which is cut from the ingot. This wafer is of what type and which silicon doping is done, which lattice is there and which silicon type is there. We use two cuts on the surface, on the diameter of this wafer. For example, one cut is here and one cut is one smaller cut is there. The larger cut is known as the primary cut and the smaller cut is the secondary cut. Now these can be anywhere on the parameter of this ring, of this plate. If the diameter has only one cut, for example here, if it has only one cut at the parameter of this circle, this is p type 111 Miller indices wafer. So now we can see that there is a more number of holes in this wafer and the orientation is 111, Miller index is 111. So all these things, all those processes which can increase the chances of volume defects, that is edge dislocation or skewing effect, those can be removed, those can be taken care of. Similarly, if this is a primary cut, and if there is a secondary cut which is smaller in this size, which is at the 90 degree, if these are making 90 degree angle at the center, then this is a p type 100 crystal. That means p type orientation is 1, Miller index is 100. Similarly, for the n type of crystal, we have two cuts. One is primary and secondary is at the 60 degree to the surface. 60 degree to the surface. So this 60 degree surface means the two cuts are adjacent to each other. So this shows n type 111 crystal. So p type has one cut and n type has two cuts, primary and the secondary cuts. Then there is n type crystal which has two cuts. One is at the lower and other is at the end, and they are making 180 degree between the two cuts. So these cuts shows that what is the orientation of the crystal and what is the how we can use it. These are the different crystal structures which we have discussed in the main lecture. So this is the crystal defects and the crystal orientation, which is required to discuss prior to the epitaxy, which is lecture 2. This must be known that when we have different orientation, the crystal parameters, crystal properties, characteristics, all this varies with the crystal orientation, and we want a particular crystal to be oriented in a particular Miller indexes only.